Okay. Well, remember, make sure Pandora's not running in the background. We don't want music on there, right? And it is. Okay, guys, let's rock and roll here, guys. We've been doing a very nice job at looking at solving multi-step equations. A lot of what we look at today is going to be very similar to what we've been doing. We're just going to add an extra step to this. And today, 1.3 is going to talk about solving equations with variables on not just one side, but both sides. In your equation, you have like an x on just the left-hand side and just numbers on the right. Today, you might have some x's on the right and some x's on your left as well. I got that wrong. X is on the left, x is on the right. Everybody agree with that? So that can happen, and that's kind of what we're going to look at today. So essential question-wise, here's what we're looking at addressing. How can you use equations with variables on both sides to solve real-life problems? That's what's most important today. Okay. Goals. How about a person volunteer to read that first goal for us in order to meet our essential question? Anybody want to read that first goal for us? Anybody? Go, Emily.
How can you use equations with variables? Wait.
That's all right. That's all right.
Oh, shoot.
You're doing the essential question again. That's okay. What goals are we going to accomplish to meet that or answer that?
Solve linear equations with variables on both sides.
Solve linear equations with variables on both sides.
Identify solutions of linear equations.
Identify solutions. So.
And use linear equations to solve real-life problems.
Doesn't this kind of sound a lot like what we did in the last section? So the idea is we're looking for a solution for our unknown variable. Okay. So solve equations with variables on both sides. Identify the solutions of linear equations. I will tell you today, sometimes some of these problems, you may not have an answer. It may not be possible. Okay. Have you guys been able to get answers in all the stuff you've done prior to this point today? Been able to, right? Today it might be different. Okay. Guys, we need a few things to remember here. We need to know basic area formulas to do what we're going to do here in a second. But guys, area is going to be the amount of square units inside of an object. Okay, and the first basic shape that I'm throwing up here is a rectangle. Anybody recall the area formula for a rectangle? Or how you find the number of square units inside of a rectangle? If I was to write a formula for this, area would equal, what if I told you that this down here is a base and this is a height, or a length and a width? Anybody know what you would do? Elisha, you got an idea? Excellent. Area is equal to a base times a height. Okay, so if I have a rectangle with a base of 4 units and a height of 6 units, what's that get you for an area, guys? How many square units would be inside there? 24 then. Okay, my area would be 24. Okay, and let me just do something quickly here. So right here, same game. If what did we say our base length was in that example? 4. Base length is 4. What was the height? 6 of them? All right, so the base length is 4 down here, and the height of this is 6. How many of these square units are inside there? If this is 4 long and 6 high? 24 of them here. So that's the number of units that you're looking at. Number of square units on the inside would be your area. Okay. So quickly here, we'll just get a couple of other formulas down that you're going to need today to be successful. Triangle. Anybody recall an area formula for a triangle? 3-sided figure. Maybe this is my base, and maybe this is, I'm sorry, I got that wrong. Maybe this is my height and this is my base. Anybody recall an area formula triangle or an area formula for a triangle? No one, you remember it?
Just BA equals B times H, or we have to divide it by 2.
Okay. I like that formula. Base times height divided by 2. Okay, base times height divided by 2. And this is true because if I go back to that example, if I would cut this in half right here, guys, what kind of shapes are formed when I cut that diagonal in there? 2 triangles. Wouldn't the area in this bottom triangle be half of what the rectangle was? Wasn't a rectangle basically a base times a height, all of it? So isn't the triangle half of that? So an area formula for a triangle, base times height, divide that by 2. Okay, and we'll look at some examples here in a second. All right, here's the big one today. Who recalls the area formula for a circle? Remember, Elisha? Pi is your value 3.14 that you're going to use it. I definitely agree with that. I've got a note right down here. I think you're talking about the distance on the outside for circumference, and we'll talk about that. Circumference, we know what perimeter is, but the circumference is the perimeter of a circle, and that'll be this formula. Okay, so that'll be the distance around the circle, but how about the number of square units on the inside? It does contain pi in there, Elisha. Anybody remember it? What kind of units does area consider on the inside? Those units on the inside were what shape? Squares, weren't they? What power is a square? If I square something, what power is that, Xavier?
Squared.
Squared. Okay. Anybody recall this formula for a circle? I'll do my best to draw a circle. Ooh, he's pretty good. It's a nice circle. Can you guys make circles that nice? Oh, all right. You remember it, Xavier?
Pi r squared.
Pi r squared. Yeah, that's how I always remember. What's that r representing? Radius. What the heck is a radius of a circle? Huh?
It's like half of the diameter.
Half the diameter. Well, what the heck is the diameter?
It's the line of distance across.
The distance across. So this would be a diameter right here. Boom.
Wait, no.
No?
You have to in the middle, like from one side to the other.
So in the middle, one side. So it's got to go through the center, you're telling me? Yeah, you're exactly right. From a center to the outer edge would be a radius. Very good. Okay. All right. So I'm going to do something here quickly. First of all, don't lose sight of the fact that I don't know if anybody made this note, but I've got to erase this, but I appreciate it. Don't lose sight of some of the stuff we've done with perimeters in the past sections, but if they ever involve area, what formulas are you going to run to? If any of your problems involve an area, what are you going to run to? Those, right? Okay. Let me do some thinking here. I'm going to draw some shapes. I want you to draw kind of the same type of shape that I'm about to draw, okay? Now I've got to think. So if you take a second, get those 2 types of shapes drawn right there. I'm going to label this an X, this distance an X, and this distance an X on those. I'll call this distance 8, 7, 2. And I gotta think here. Pictures might not be drawn to scale, just keep that in mind, okay? I was graded on my math abilities, not my artistic abilities. You guys saw my airplane, like, was it this class I drew an airplane? Oh, no, I'm good, but you didn't see my airplane. I wouldn't want to be on that airplane or you wouldn't in the class. Okay, here's a front-loading question. I want you guys to kind of think about this. I'm not going to give you the answer right away, we'll come back to it, but here's the deal. It says the two shapes have the same what, guys? Perimeter. It says find the perimeter of each polygon, okay? Now in each polygon, you have some distances that you know and some distances that you don't know. But the big idea here is that the perimeters are what? Same, okay? Anybody have a thought on this maybe about how you would go about solving something like this? Oh, I know. What's the distance around each figure? If I told you the distance all the way around the one on the left is 50, what would that have to imply about the distance all the way around the one on the right? It would also have to be 50. Okay? But you guys take about a minute and talk with somebody about that and let me know what you may or may not do. Anybody have an idea? And if you get a solution, I suppose I better do this problem too. I think I've got a perimeter for each one. Take a minute and talk about that with somebody. Again, keep in mind, are these necessarily drawn to scale? Okay, anybody have any thoughts on this? Any ideas about how you might go about solving something like this? Libby, what do you think? Okay. What's that equation look like for you? So, what's your expression on the left? What do you have for an expression on the left? I'm going to write it right inside the box. 2x plus 17. Libby, is your 2x plus 17, again, it's perimeter, so I'm counting around here. How many x's on the outside here, guys? There's two of them, right? That's the 2x part. And then the 8 and the 7 and the 2 add up to how much? What do the 8 and the 7 and the 2 add up to? 17. Okay, how about your other one here, Libby? Okay, and I'm going to call this x plus 28. You're exactly on the right track here. Now, here's the deal. What was given in here, these are the expressions for the perimeters, and we told you right here the shapes have what? Same perimeter. Okay, so what am I going to do with the expression on the left and the expression on the right here in the end? We're going to set them equal to each other, right? Libby, that was excellent. Great explanation. I'm going to come back to that. We'll finish this up after we got the process down, but we'll come back to this. But how many think Libby's got a pretty good plan to go ahead and attack this one today? Think around, look around, Libby. Excellent, excellent. Okay. All right, so let me get rid of this here. Let's roll on to the second page here quickly. We'll start rocking and rolling this. Guys, rules to solving equations with variables on both sides. Hey, this is a pretty important menu. Doesn't that menu look pretty similar to what we had in the notes, section 1.2 in terms of solving equations? Okay. Now again, keep in mind, we're looking at variables on both sides here now. So the rules go like this. Step 1, rewrite if necessary. Does that sound familiar? Step 2, distribute if possible. Does that sound familiar? 3, combine like terms on both sides of the equation. Does that sound familiar? Okay, here's what's new for us. What's really going to be new for us is right here. We have to get variables to what? What's it say? Step 4, get variables to one side. I don't care if you get them all to the left or all to the right. It doesn't make any difference. And I'll show you how to do that here in a second. Step 5, does that look familiar? Step 6, boy, I did a poor job in the last section, but undo multiplication, division, or this fraction means if you have like a 3 over 5x, how do you undo that 3/5 out in front, guys? Multiply by the, what's the word I'm looking for? Reciprocal. Okay, multiply by reciprocal, and we'll see some. So, let's jump into this. Let's look at some solving examples. Let's look at some solving examples. Guys, example 1 here. Here we go. 2x plus 14 equals 3x plus 10. First of all, I'm not going to rewrite this. Okay? The x's are both out in front. The x is out front here, and the x is out front here. I like that. Any parentheses to deal with? Okay. Look at just the, hang on a second. I'll play with this one here. Just look at the left side like this. Anything I can combine right here? Anything I can combine on here? Okay, look at the right side of your equation. 8. Anything you can combine on the right side? No, so I can't combine terms, so real quickly, here we go. The third step says get variables to one side. I don't care how you do this, all right? What I need to do is consider the variable to one side. I like working from the left, so I like to get all my variables to the left. So I always go to the right side and say, hey, are there any variables on the right side? Looking at the right side here, are there any variables? Variable's 3x, right? What kind of 3x is that? Positive. Okay, so if I had to ask you guys to get rid of a positive 3x, what might be a process, or what might be an inverse for getting rid of a positive 3x, CJ? Subtract, okay? So this is the part where we say, you know what, we can also subtract variable terms like this instead of constants. If I subtract 3x on the right, I better do what on the left, kiddos? Right? Help me rewrite the left-hand side now. Here you have a 2x minus what, guys? 3x, which is negative 1x. What's still on the left side? So I've got to put a plus 14. On the right side, my 3x's are going to, they're going to get dumped out of there. And what are you going to have on the right side? Okay. I went from an equation with variables on both sides to an equation with variables just on one side, the left in this case. That's okay, isn't it? We know how to solve those, so run me through this quickly. Next step. Excellent. Negative 14 on both sides, and I'll quickly run through this. 14s are gone. You have negative 1x equals. What's your last step then, kids? Divide negative 1, and what's your quotient here, Kelly? Positive 4. I've got x equal positive 4 when I'm done with this. Okay. Now, guys, you may or may not want to write down what I'm going to put here second. It doesn't matter. If you're okay with this, I would say it's probably don't need to. But I'm going to rewrite the problem. And I'm going to rewrite it as 2x plus 14 equals 3x plus 10, just like it was. Guys, the first step that we took was to subtract 3x from both sides, right? I said I like to get rid of stuff on the right, but is it possible to directionally say get variables to one side, right? Maybe I did it the other way. Instead of subtracting 3x, maybe I said, I don't like this 2x here. What could I have done? Minus a 2x, okay? Okay, so what's this look like? Well, you would have 14 on the left, wouldn't you, kids? What would you have on the right? X plus 10, 1x plus 10. So my next step would be to subtract how much? 10. When I subtract 10, what do you get? How do these solutions compare? Same thing, aren't they? Same thing. So does it matter what direction you go if you have variables on both sides? you're still going to end up at the same place, right? For me, it's if I'm going to a Twins game in the summer, am I going up I-35 all the way, or am I going to take Highway 52 all the way up all the way? Bottom line is Target Field's my destination, right? Right? Okay. All right. So let's try an example here in 2 where we're looking at solving an equation with grouping symbols. Same thing, same exact thing. Follow your rules. How about a volunteer to start me on this? Volunteer to start me? Go, Kaylee. So we've got 9x minus. All right, you're on a roll. So that would be 1/4. So 1 times 32 divided by 4. Can I just tell you 1/4 of 32 is 8x? Is that okay? Plus what? All right, Kaylee, pick someone different to talk me through the next step. Who wants to help me? Who can? Natalie. Natalie, I have variables on both sides, so which one do you want to move? You want to move the 8x or do you want to move the 9x? Okay, so what kind of 8x do you have, Nat? It's positive, excellent. So what should I do to both sides? All right, so let's subtract an 8x here. Subtract an 8x here. All right, 9x minus 8x is, I know that's 1x. Still with a term up here, constant term, minus 12. Natalie, on the right side, what will the 8x's do? Okay, Nat, you want to finish it up for me?
Then you add 12 to both sides. That would be 1x is equal to 19 divided by 1.
Very good. Okay. So far, we had solutions in both of these equations. Remember, I prefaced this by saying, you know what? Some of these problems may not have an answer, right? Okay, so let's look at something like this. First things first, do you guys have everything down on that page right there? Are we good? All good? Okay. Got it all, Mason? Let me know. I saw smoke coming off that pencil. You're writing so fast. Everybody have it? Well, this is an interesting one. All of a sudden it says you have equations with what? No answer here. Absolutely no answer. All right. Check this out. Equations with no solution. Okay, let's just start the work right here. You guys are going to have to distribute on the left, right? So you agree 12b minus what? Equals 12b. I want to show you something, okay? I want to show you something right here. In the previous examples, I'm going to go back to the last page. In the previous examples, notice your variables on both sides. The term I'm going to use is called a coefficient, a number in front of a variable. Here in this problem right here, you have a 2x and a 3x. Are the coefficients 2 and 3 exactly the same? Or are they different? Are the coefficients 2 and coefficient 3, are they the same or different values? When it was different here, did we get an answer? We did. Same thing here. Coefficients the same or different? 8x, 9x. They're different. Did we get an answer for that? Okay. Real quickly here, guys. What do you notice about your coefficients up here this time? They're exactly the same. Okay. Now, that doesn't mean if the coefficients are the same, there's already no solution. I want to show you what's going on here. This is how we get to that. Okay. I don't like this 12b over here. So what are you guys going to do to both sides? Subtract the 12b. Now, be very careful on stuff like this. In this problem, you might want to put a star by and pay some close attention to what I'm about to tell you. You guys ready to roll this? What do 12b's do to each other right here? They actually cancel. They're gone. And what are you left with? Okay, so the variable D is just gone, and that's it. Okay, no problem. What happens on the right side? They cancel. Okay. Oh my God, there's nothing left over there. Guys, what value do we use in math to represent nothing? 0, right? 0, right? On both sides, when I add the same coefficient to your variable, the variables dropped out of both sides. Meaning, can I even solve for D in the first place? I can't. And all of a sudden I get this statement that says, hey, -4 is equal to 0 now, guys. -4 is equal to 0. Does that make any sense? Does that make any sense? Okay? My wife is always running around the house every day when I say something. That doesn't even make any sense, Justin. That doesn't even make any sense, Justin. That's what she says to me all the time. If you get something like this as just, for lack of a better term, this is totally crazy, right? What? Okay. Is that not used anymore? Well, how far behind am I? Couple of years? Oh no! Alright, well I still like cray. Does that make any sense at all? -4 doesn't equal 0. So what I'm going to say here is there is no solution. Now I want to show you something. I think that this can make better sense here. But yeah, you know what? I'll come back to it. Something like this, we would say there's no solution. When the variables drop out of both sides and you get a false statement, -4 will never be 0. So it's just saying there's no value of D that works here. Okay. Now, example 4 is kind of the same thing. An example with what here, guys? Well, what's it say here? Many solutions. Help me out here, guys. 8 times 2x. What's the 8 times the 2x? What's the 8 times the 6? Okay. Well, I've got 16x on both sides, so what should I do? Subtracting 16x from both sides, right? And when I do that, what do you get on the left side? So this is going to cancel, but what value is still here with the 16? 48. On the right side, what are you going to be left with? Oh boy. Same exact thing as what happened up top. This time, the variables dropped out of both sides because the coefficients were the same. However, unlike example 3 where the comparison in the end didn't make any sense, what's true about the comparison down here? They're the same this time, right? Is that crazy or is that okay? That's okay. 48 is equal to 48. So if you get into a situation where D just, or your variable just drops out everywhere, this is a case right here where you say you would have many solutions. And kind of what I'm getting at is this. If I would put a 0 in here and a 0 in here, aren't you going to get the same answer? Wasn't the expression 16x plus 48 the same as 16x plus 48 over here? If I put a 4 in for x here and a 4 in for x there, won't I get the same output? I would, wouldn't I? Okay. So here's what I want you to do. On your own, I've got 4 problems. Take a couple minutes and try those. And then I'm going to show you some kind of a graphing utility that might be beneficial to you. Just show you what's going on here. But just take a couple minutes and run through those. And then when you've got those answers on those on your own down there, check with the neighbor and see if you guys agree. If you don't get all the way through them, that's fine. right, who wants to be a volunteer to do the first one here? Kelly, have you got it? I want to show you something right here. You're going to want your Chromebook open. I'm going to have you get into a website today to maybe help you check some solutions on this and kind of give you a little bit of a pointer. Okay.
What I did first is I added 3p to both sides. And then I got 8p equals 24. And then I divided by 8 both sides. And then I got p equals 3.
I'm going to agree that p is equal to 3. Okay, here's what I want you guys to do. Thanks, Kelly. Excellent. In your Chromebook, go ahead and type this in, www.desmos.com. And I want you to bookmark that page because you will use it a ton. All right? Desmos.com. Everybody there? And then I'm also going to make a note here for you guys. What variable did I use in this problem up here? Best letter in the alphabet. P. When you get into Desmos, I always want you to change your variables to X. So no matter what the variable is here, you're going to put in what in Desmos? X. Do you have a part there that says launch the calculator? Do that for me. Okay, here's what I want you guys to do. We originally had, what do we have? 5p equals 24 minus, was it 24 minus 3p? Now again, I think that's pretty simple and pretty basic. And you'll be doing pretty well with this. But when things get more complicated, this might be an excellent tool to help you check solutions. Do I still want to see work from you? Absolutely. But this is going to put your mind at ease when you do problems like this. Do this for me. And the top one right up here, just write 5x, which is like the 5p on the left side of the equation, right? Make sense to you? Anybody have that? Then do this for me. In the second box, don't worry about what I have on number 2. In the second box, type in 24 minus 3x for me. Okay, now does your computer kick out a graph at you? All right. You may have to zoom out a little bit. So go ahead and hit the minus sign up here, zoom out a little. And then describe to me what happens to those lines when you put them in graphing form. Do they cross or not cross? They cross, okay? You see this point where they cross at? Click right up here on that point. Oh my gosh. What's the first value up there? 3. What was our solution to this problem? 3, okay? You'll always use the first value here to determine what the solution is. That first value should match what you've got on your work. So if this first value doesn't match, something's got to be what? Wrong, okay? Something's got to be wrong, all right? So if that helps you, use it. If it doesn't help you, then don't use it. I'm going to look at the problem right below here, guys. This is the problem right below. 3 times 5x plus 2 equals 15x plus 12. Give me on your own. That's the bottom left one, right? 3 times 5x plus 2 is equal to this. What happens to the lines right here when I graph them, guys? Do they ever cross? They don't cross. Do they share a point? Do they even share a point? They don't. They don't cross. What'd you guys get for your answer on the bottom left? No solution. No solution because graphically your lines don't do what? They don't cross. They don't share a point. If they don't share a point, there can't be a solution. That's what this tool is used for, okay? All right, so quickly, I want to run through those. All right. What was that? All right, so let's run through this top right one right here. Tell me if my distributions are right. 6n. Whoa, don't want to do that. How about this? 6n minus 8. Am I right on the left? What's half of 10, gang? 5 minus 0.5n. Okay, what step did you take next? Anybody? What'd you do, Emily?
I added 0.5 n.
Add 0.5n to both sides. So on the left side, you would have 6.5n minus 8 equals 5. I agree. Then what'd you do?
Then I added 8 to both sides.
Which is 13. And then took 13 and divided by?
6.5, you get 2.
Should get a nice value of 2. Okay? So if I were to put those in there as lines, what would that point be? What would the first value of the point where those lines cross been? 2. Okay. This one here, what'd you say here?
Oh, no solution.
It's all right. 15x plus
6.
this one's going to either be no solution or many solutions because the 15x's are the same on both sides. You're going to end up with 6 on the left and 12 on the right. Those values match or are they different? So this is a crazy problem. So we would say no solution. Okay. Check out the next one here, guys. You have 21 minus 7w equals 21 minus 7w after I distribute, right? Are the coefficients the same on the 7w's? They're both negative 7, right? So what are you going to do? Both sides? Add a 7w. When I add 7w, I've got 21 is equal to 21. So what's this implying? Many solutions. Okay? Many solutions. Guys, many solutions in graphs would look like this. You would have one line, and you would be graphing. Aren't you really graphing the same exact thing right here? Part 1 and part 2. You're going to have one line, and then the second line would fall right on top of that. So how many points are shared if one line falls right on top of another? All of them. So many, right? Okay, good. How many are okay with the on your own's part? You can solve these and do okay with it. Perfect. All right, let's run through the one that I think is difficult here. You'll see a story problem pretty similar to this. Here's what it looks like, kids. This problem, when I wrote it last night, I kind of got to laughing about it. Paul bikes for 3 hours to reach his favorite beach. Hopefully there's a beach at the end of Ragby, right? 3 hours on a bike. I don't think my arse can take it. All right. How many of you guys like to ride a bike for a long time? I like to ride a bike, but hurts the bottom. All right. Paul rides a bike for 3 hours to reach his favorite beach. He bikes 2 miles per hour faster on the way back. So the trip back takes, that should be only right there. Takes only 2.5 hours. Okay. How fast did he bike going to the beach? All right, I'm going to draw kind of a little picture here. A little picture. I already told you why a bike can't stand on its own, right? How's my bike? Thank you. I think it's pretty nice. Okay, you start here. You go to the beach, where there's maybe some sand and some palm trees. Looks like fireworks coming off a tree, but that's okay. And you're going to spend time at the beach, and then on your trip back, you're going to end at the same spot, right? What's true about the distance going to the beach and the distance coming back? It's the same, okay? Let's write some stuff down. Going to the beach, what do we know about his trip to the beach? It took him 3 hours, okay? Kaylee, question? Oh, thanks, 9:15. Let me finish this up. It takes 3 hours. Anything else we know about the trip on the way over? Don't have a clue, do we? Okay. Then, how about the trip back? What do you know about the trip back? Bikes 2 miles per hour faster. Anything else about the trip back?
It takes
Only 2.5 hours. Okay, so the thing that we're trying to figure out, so we want to know how fast was he going on his way to the beach? How fast was he going on his way to the beach? So We don't know how fast he was going, the speed. Now I've made a note up here, guys. In science class, you've probably talked about any distance that you travel is equal to a rate times what? Rate times time. The distance going to the beach would be the same as the distance coming back, right? Everybody agree with that? Okay. So what we're trying to do, and what I'm going to say is this, we're going to let R equal his speed to the beach. That's what we're trying to find. I'm going to let R equal the speed going to the beach. Okay, so here's the deal. Let's write an expression for the distance going to the beach. Again, how is distance defined? Rate times what? Time. Okay, do I know his rate up here to begin with? Going to the beach. I don't know it, so we call it what? R. Do we know his time? 3 hours, right? So what would an expression be if I was taking a rate times a time here for going to the beach? 3 times what? R. Okay, 3R. That's going to equal the distance back, going back, which is the rate times the time. Do we know his rate at all? We just know he was 2 miles an hour faster, right? He was going 2 miles an hour faster. So if he was going out at a rate of R, what's 2 miles an hour faster, or the expression for 2 miles an hour faster? It would be R plus how much more? 2, wouldn't it? Isn't his rate going to be that same rate R plus 2 miles per hour more? Everybody agree with that? He was going 2 miles an hour faster than the one he was going to the beach, right? How long did it take him? So the time would be 2.5, okay? So here's my rate times my time over here. We just spent a bunch of time talking about writing equations with variables on both sides. I modeled this situation with an equation on both sides, right? Okay. So what I would ask you guys to finish up for the notes here is this. Try and solve this problem for R. Once you find R, that'll tell you how fast he was going on his way to the beach. Then, I also want you to come back to this first one that Libby had a great start on and tell me what the perimeters of these two shapes are if you set this equal to this. Okay? One thing I want to check on here, just to make sure I'm perfectly okay, is your 1.2 before you leave. Don't leave it with bell rings. Let's see, Taylor, were you able to get the 1.2 done then? Okay. How much of it did you get done? You still have it open? Okay. I'll talk to you in a second. Dylan, were you able to get it finished?
No.
Okay, how much do you have left? What's that?
I didn't get
Okay. What's that? You have it done? Okay. Elisha, you were working on it yesterday. He's pretty much done, right? And then last one, Noah, did you get through most of it? Did you get through most of it? Okay. All right. Have a good day, guys.